Now let's see how we can calculate these invariant matrix element M, or the matrix element of T, from initial state, final state, which we had defined as the overall four-dimensional energy momentum conservation times Im. Let's see how we can calculate this matrix element and also obtain M using the Feynman diagrams. Now let's start with the definition of T. If you remember, we had defined this Ka, Kb, ingoing states, K1 up to Kn. These are the outgoing states. This was how we had defined the T matrix element. So this T matrix element, and if you remember how we had defined these states, so we had the from the zero state, we first created the Ka and Kb particles. Then we evolved them from the time minus t to the time t. And then this state over here was just the, if we take the bra, it will be phi k1, phi k2, phi kn, 0. And keep in mind that the normalizations of these states were such that we had this, this factor, and then it is multiplied by square root of 2e kf over all particles, and square root of 2e, let's say kx, when x is a or b. These are just the our normalization of the states. These give us the normalization. Now we had already seen that. Let's just look at this matrix element over here. Now we had already seen before that this matrix element can actually be written in the interaction picture as a time-ordered product of phi of k1. Remember, now these operators are acting at the time t. Time-ordered product k at t, phi k2t, phi kn of t. And then these operators are acting at the time minus t, phi dagger of ka minus t, phi dagger of kb at minus t. And then this just became the time ordered exponential, since everything is in the time ordering, e to power minus I from minus t to t, h, the interaction part of the Hamiltonian at the time t dt. And remember that we will eventually take care of these square root of two factors. So this is the matrix element appearing in the T. Now this is almost similar to what we had before when we were discussing Feynman diagrams. But remember, before we also had another, we already know the Wick theorem. So now we can use the Wick theorem to calculate all these factors. But let me just divide this factor by, let me just write an equality with a dot, meaning that they need not be equal, but they are equal up to a phase. So we have all this term. I will just divide this term by the matrix element of the time ordered exponential. And remember, this just told us that when we have this ratio, the Feynman diagrams we need to take into account are only the Feynman diagrams that are connected. Phi k1 of t, phi kn of t, phi ka dagger at the time minus t, phi kb dagger at the time minus t. Now here we should be calculating only the connected Feynman diagrams, not all of them. Now the reason why we can actually divide by this factor, and still we can use the definition by dividing by this factor, is that, as we will show shortly, this factor is nothing but a phase. So to see that it is actually a phase, let's look at how we had actually defined these in states and the out states. Remember, even in our earlier discussions, we defined these in states and out states in terms of the non-interacting vacuum. And we were using the non-interacting fields, annihilation and creation operators. In fact, when we were doing that, we were actually making a so-called adiabatic approximation. Which we are essentially saying that at the time t is equal to minus t, which goes to minus infinity, there is no interaction. Well, the particles that we are interested in are already far away, so this doesn't really, they are not really interacting anyway. And then we turn on the interaction adiabatically. Turn on the interaction adiabatically. So we have our particles that are far away, then they are approaching each other, where they are far away at the minus infinity, they are approaching. As they are approaching, we are also turning on the interaction, so when they can actually interact, there we have the full interaction of the theory. But this adiabatic changes make sure that if we start with a two-particle state, like this one, adiabatic theory just tells us that whichever state you start with, if you change your theory adiabatically, the state still stays in the same state. If, for example, in the case of quantum mechanics, if the state you start with the state in the nth state, and if you turn on change your interactions adiabatically, it will still stay in the nth state. Of course, the nth state might be different, but nevertheless, it will be in the nth state. So similarly, if we start with two-particle state and turn on the interactions adiabatically, our state will still be the two-particle state when the particles start interacting. And then we turned on the interaction adiabatically, scattering happens. And then we turn off the interaction. Again, adiabatically. So that we can actually also define, just like we define the in states, we can define the out states in terms of the non-interacting theory. But this also tells us that if you start with the vacuum and let it evolve from the time minus t up to the time t, with the Hamiltonian keeping in mind of this, taking care of this adiabatic turning on and turning off the interaction, this state, when we turn on and off the interaction, since we started from the the ground state of the non-interacting theory, we changed the theory, we turned on the interaction, then turned off the interaction, eventually we ended up having the non-interacting theory, and since we started from the vacuum, this will still be the ground state of the non-interacting theory. And keep in mind that we are of course taking the limit as t goes, this capital T goes to infinity. But of course, the adiabatic theory only tells us that it will stay in the same state. And the only possible change in this state is just a phase, some unknown phase. Now, this tells me that this 0 e to the power minus I, t minus t, h0 is actually a phase. But since it is just a phase, and eventually I will be interested in calculating the square of this T matrix element. I can just divide this matrix element by t, by this phase, and its absolute value will not change. And it will save me a lot of computation because by dividing that factor, I only take into account the connected diagrams. Now let's see how we can calculate these connected diagram, connected Feynman rules. So let me just take this. And I will take the limit that t goes to infinity. Let me just write it in this form. Phi kn, phi ka dagger, phi kb dagger, e to power minus I d4x. Now this is the Hamiltonian density. Only the connected diagrams. And although we have this time ordered product, just keep in mind that these dagger operators are before in terms of time, they act before any of the other operators, and these operators, they act after any of the operators. So, but since this is a time ordered product, we already know how to calculate the time ordered product of operators in free theory. We can use the Wick theorem. The only ingredient that we are missing is the contractions of phi and phi dagger with the other fields. So let's calculate them. Let's calculate what is the contraction of, let's say, phi dagger, any vector, any momentum k with phi of x. Remember, here in h in, most of the time you will have fields of at the time x. And to calculate this time ordered product, let's try to remember how it appears in the Wick theorem. Let us just consider the time ordered product of these two fields. The time ordered product becomes the normal product, phi of x, minus the contraction. So that contraction, plus the contraction, that contraction of phi k dagger and our field at the point x is just the time ordered product minus the normal ordered product. Now this is equal to, keep in mind that we had already said that this dagger operators are acting before any other operator appearing in this matrix element. So you see they are at the minus time t, and all the operators appearing in the interaction Hamiltonian are after this time minus t. So even if we take the limit t goes to capital T goes to infinity, we should keep that in mind. These always act before any of other operator. This phi x is coming from this interaction term. So since this is acting before any other operator, this time ordered product is actually phi of x, phi k dagger. And if you look at this normal ordered product, remember what the normal ordered product does. It puts the creation operators to the left and annihilation operators to the right. So in this form, the creation operators are already on the left. So this is minus phi k dagger, phi of x. So the contraction of these two fields is, let me just rewrite it. This is just the commutator of the field at the point x and the phi k dagger. Now we already know what the form of phi of x is. Phi of x can be written as a Fourier series d cubed k divided by 2 pi q, 2e k, phi of k e to the power minus I kx plus phi of k dagger. Well, let me just use this integration variable p, not to confuse with this k over here. This is p, e to power I p of x. These are at the time with momentum p. Now if we calculate that commutator, this will be equal to d cubed p divided by 2 pi cube 2ep, the commutator of phi of p and phi k of dagger e to power minus I px, and keep in mind that phi p dagger commutes with phi k dagger for all values of p and k. And again, let me also write down the time here. This is at the time minus t. And keep in mind that this operator at the time minus t has a factor of e to power minus I ek minus t. Now since at this dagger we have a plus sign. So if we, this commutator, we had already studied it, it is just 2 pi cube times the 3-dimensional Dirac delta of p minus k. And so in this field, this is square root of 2ep. So this contraction is actually equal to this 2 pi cube cancel this 2 pi cube 1 over square root of 2ek e to the power minus I k of x e to the power I ek of minus ek of t. So first thing to note is, you see, we have this 1 over square root of 2ek, k being the momentum of this field. Now if you go back to the matrix element that we are looking for, at the end of the day we want to calculate this matrix element over here in the T matrix, multiply by square root of 2eka and kb. So since we calculated the contractions of these ones, the contractions of these ones will bring factors of 1 over square root of 2eka and 1 over 2 square root of ekb, and those 1 over square roots will cancel just this factor over here. Now let's look at these terms. What will be the contraction of these terms? So we have similarly, let's look at the time ordered product of phi k, not the dagger this time, with phi x. This will be equal to the normal ordered product of phi k and phi of x, and keep in mind that these are at the time t. And plus their contraction. So their contraction of phi of k of t and phi of x will be equal to the time ordered product. But remember, this operator acts after all the other operators. So this time ordered product is just phi of k of t, phi of x, minus this normal ordered product. And remember, the normal ordered product just puts all the annihilation operators to the right. So this normal ordered product is actually phi of x, phi k of t. So this contraction is actually the commutator of phi k of t and phi of x. And again, phi of x is equal to d cubed p divided by 2 pi cube square root of 2ep, and then we have phi of p e to the power minus I kx plus phi of p dagger e to the power I kx. So the contraction of phi of k of t, phi of x, is equal to d cubed p divided by 2 pi cube square root of 2ep. Now this phi of k commutes with phi of p, and then we have phi k of t and the commutator of phi k of t and phi p dagger. phi k of t has e to power minus I k, no, ek of t. This is the time dependence. And then we have, since we are looking at this term, we also have e to power I k of x. No, p of x. Here these are p's. And this commutator is again 2 pi cube, the three-dimensional Dirac delta of k minus p. So this p integral just gives me these 2 pi cubes cancel. I can take this p integral using this Dirac delta, and it just gives me e to the power minus I e k of t, e to the power I k of x divided by square root of 2 e k. Remember, and keep in mind again that now we also have another 1 over square root of 2 e k for each of the phi k operators. So if you go back to our initial matrix element over here, contraction of these fields brought us 1 over square root of 2 e k a and 1 over 2 square root of 2 e k b, and they cancel this one. And the contraction of these brought us 1 over square root of 2 e k f for each one of these k1 to kn, and they cancel this one. So eventually these factors, they all cancel. And so let's write down the T matrix element. Well, let me just copy our expression. It was this expression over here that we are trying to calculate. So this brought us these factors cancel out. Now all these fields, if we want to get some non-zero matrix elements, all these fields should be contracted with something from the Hamiltonian. And when we have those contractions, we will have e to the power I k f x f for each one of these phi fields, that each one of them corresponds to the out particles. And then we have e to the power minus I k I x I, these k i's corresponding to the ingoing particles. So for each ingoing particle we have an e to the power minus I k I x I, and the outgoing particle we have e to the power I k f x f, and then we have all these exponents. We have e to the power minus I e of k f of t, and here we have e to the power minus I e of k a of t. But keep in mind that again these are just phase space factors which will appear in all the diagrams, so we can just ignore those factors. These are just overall factors. And then we have the remaining remaining terms in the Feynman diagram. Now keep in mind that these xi's and xf's, they are the positions of the interaction vertices. They come from, you see, if you look at this time ordered expression, the way we calculated this time ordered product was we just Taylor expanded this. So we have for each vertex has a position, and when these fields are contracted with a field at the position x, they bring down a factor of e to the power ikx or e to the power minus ikx. So essentially we can augment our earlier Feynman rules by saying that if we have an ingoing particle with a momentum k, ki, this is an ingoing particle, Let me just show it by an arrow. It's an ingoing particle. It is connecting to a vertex at the point x. This corresponds to a factor e to power minus I kx. And if we have an outgoing particle, that appears from a vertex at the point x, this will give us an e to power plus I kx from these exponents over there. So these are the Feynman rules that will allow us to calculate the scattering cross-section amplitudes.